Okay, so welcome everyone to this new episode of EagleFly, the experimental debugger. Uh, well, for today, uh, today we're gonna continue looking at the IF32 architecture, and yeah, what a better day to do that? So let me go back and open the file. Well, I already had it open, so good. And let's continue. Please, I forgot. If you have any questions about what we are doing on this project, or you have any kind of inquiry, you can ask it, and I'll be open to answer any questions you have. Feel free to ask them on YouTube or Twitch or on Twitter, and I'll be happy to answer them. That's interesting. So we use like the 32 bits registers for addressing linear address space inside a program, which that makes sense. So it depends, but I mean, what you could do, for example, if you're using a linear address space, is that you can have different segments registers to point different spaces inside your program space. Also, I mean, so if every program that's executing is using these segments, how does they manage? How does they organize? You know what I mean? Because, for example, one process can be modifying the segment registers, whilst the other process will need that segment's data. So it will be like loading and unloading all the time, you know, I'll assume. But let's say right now that we just have a process, okay? But that's kind of a intriguing question. So if we use linear address space, they will be overlapping. So we don't have any control. Well, we can have control of, but we will need it to do it programmatically, so that each segment doesn't overlap each other. If that's what we would like to. In that sense, it would be better to have the segmented memory model. Oh, okay, okay, okay. So you would combine the pointer in the CS register and the EIP pointer that's in the EIP register to find and fetch data from the code segment. Okay, so we cannot modify the CS explicitly, but it's loaded implicitly, whereas the SS register can be loaded explicitly, and that's really powerful, because that permits applications to set multiple stacks and switch amount down, which that would be like for example, like a function call or something. Can be an example of switching across stacks, but that would be like pushing on the stack, isn't it? It's a call to push on the stack. Something like that. See section 3.3 memory organization for an overview how the segment registers are used in real address mode. Okay. So, I mean, the main point for having segments is that so you can have different data structures in each segment. And that's just for some kind of practicality, or some kind of functionality there that you can so you can segment and separate different data structures inside your process. Okay, so in 64-bit mode, everything is flat, so they are not. I mean, all the offsets are treated as from the 0, which makes a linear address space. Make it flat, except for FS and GS, that they can be offset from 0, so they can add additional base registers. Bits 1, 3, 5, 15, 22, 30, 31 are reserved. there are no instructions that allow the whole register to be examined or modified directly. When suspending a task using a processor's multitasking facilities. Okay, interesting. So there's a difference between a task and a processor stack, procedure stack, sorry. So when there's an interrupt, the processor saves the flags register onto the processor's procedure stack, but when an interrupt or exception is handled with a task switch, it's saved into the TSS. And these are the bits itself, the bit flags, which is 22 to 31, they are not used, and all the gray ones are not used at all by the application. So we can use all of these ones. There's the ID flag, the virtual interrupt pending. There's the virtual interrupt flag, alignment check, access control, AC, virtual 8086, mode, resume flag, there's a nested task, higher privilege level, overflow flag, cool, direction flag, interrupt enable flag, can be the 4 interrupts themselves. There's a trap flag, there's a sign flag, the 0 flag, then there's the carry flag, and the auxiliary carry flags, and the party flags. Most of them are system flags. There's just one control flag, and there's like about 6 status flags. And the gray ones, we always have to set them to values previously read, you know? Or they're always set to values previously read. Okay. I don't know if it's that's like an order, or it's more like just a statement that it's gonna be happening. Yeah, I don't know, but we have to check that. If flags register. Okay, so first are the status flags. They are 6, and they are the bits 0, 2, 4, 6, 7, 11, and they indicate the results of arithmetic instructions. Okay. So the carry flag, it's used whenever we like kind of overflow. it's also used in multiple precision arithmetic. Okay, so it's for floating point arithmetic. I don't know. Then there's the parity flag. Hold on a second. ¿Sí? Okay. So what we left off was, okay, the status flags that basically just have this kind of handle the results for arithmetic operations. So why does, I mean, my question now should be like, why does, I mean, it's kind of a I mean, why should we know that the least significant byte has another even number of bits of 1 bits or bit set. I don't know, there's something that I haven't checked or I don't understand, so that's really important, I'll assume. So there's a pi flag, and that basically tells us if there's an even number on the less significant even number of bit set on the least significant byte. Then there's a carry flag, that's an auxiliary for the carry flag. So the auxiliary carry flag, it's used on binary coded decimal arithmetic. That I don't know how it works, but it's basically for that. Zero flag set if the result is 0. Okay, that's cool. Okay, set equal to the most significant bit of the result, which is the sign bit of a signed integer. 0 positive, 1 negative. Cool. Then we have the overflow flag. So I mean, if you think about it, I mean, all these kind of things is the kind of things that I want to know when I'm debugging. You know, I mean, when I'm debugging, we haven't opened this yet, but let me do it because why not? I mean, if you think about it, it's kind of pretty much kind of basic and essential thing about. I mean, it's not like uh, to have some kind of uh, all the things that the architecture itself tells you, so that we know what's going on, you know. So for example, if we're running on a process, we can see all these flags. I mean, it would be really nice to have the debugger itself to show you all the flags, the status flags, control flag, and the other flags. I don't know, it was the and the system flags, so you have a better idea of what's going on, you know. Because I mean, believe it or not, one of the kind of harder bugs to find is like whenever you don't have a clear understanding of what the compiler did to generate the instructions, so that you have to go to the disassembly and look at, okay, this is the kind of thing that was going on, you know. And also even also equally important is to check these kind of flags, because this can tell you a lot of good information, like overflows for arithmetic operations, and I don't know, many more stuff, you know. So yeah. Okay, so STC, CLC, and Siemens instructions can be used to modify CF bit of the E flags, and that's the only one that we can modify. That's okay, because we don't need to modify them at all. I mean, we just we just want to read them, so to make sense of what's going on the practice or instructions. So this is an overflow for two's complement sign integer arithmetic. Okay. when performing multiple precision arithmetical integers. So these instructions, JCC, SCTCC, and loopcc on condition code use one or more of the status flags as condition codes and test them for branch. Okay. So basically, these flags are used for these three different data types: sign unsigned integers and the BCD integers. Across different flags that can be CF for unsigned. It's OF for signs and AF for BCDs. So probably a carry is like some when you add two values, two operands, and the result is something out of bounds, that cannot be represented in the operand itself. Is gonna set this flag, and it depends on the type of the result. Is gonna set it on it either on the CF flag or the OF flag or on the AF flag. So it can be something more yes, or something like that, I guess. A carry or borrow for subtractions or something. And you can use add with carry and subtract with borrow. So the values that are missing, they persist in several computations, so the value doesn't get lost. Then the df flag if I remember, df flag was a control instruction. Yeah, basically df flag tells how to process string instructions as move string, compare string, scan string, load string, and store string. Man, I mean, these names are really straightforward. uh, all of them works with a string, and the only thing, I mean, what df flag tells you is like, oh, if it's set, it will auto decrement. So we process them from the higher address to the lowest address. And vice versa if the flag is not set. And we can use std and cld. So probably like string decrement, so we can decrement, or clear decrement. Okay, cool. So let's see the system flags in the IOPL field. Okay. So here's a special one, man. This is the one we were looking for. The trap flag. The trap flag lets you to enable single step mode for debugging, and clear to disable single step mode. So if we want to enable single step mode, we can set the trap flag, but well, we cannot because we cannot modify by application programs. But I'll assume that if we call something like Windows kernel to do this job for us, it could. I mean, it depends, because if we run as a kernel mode, probably we could. I don't know. So we can modify the privilege level for I operations for the process with the instructions BOPF and IR return. So my question is, what is a task? What is a task inside the process, inside the processor? So there are control registers that I don't know where they are. Set indicator interrupt is pending. Clear when interrupt is pending. Okay. Jesus. The instruction pointer register contains the offset in the current code. Segment for the next instruction to be executed is advanced from one instruction boundary to the next in a straight line code, or it is moved ahead or backwards by a number of instructions when executing a jump on code control, a call or return, and IR return instructions, which I return instructions is the one that we have here. That's good for, let me find, okay, it's gonna take a while this thing to go. It doesn't matter. It was something here that we can use iret to set some kind of flag. Well, it doesn't matter. But yeah, I mean, we can use these instructions to basically modify the instruction pointer, and that's what a process basically does. I mean, a call is a call to function. A ret is a return on a function, so we can pop up the stack, and I return is basically the same, I guess. see chapter 3, protecting mode memory management. Okay, so here it says that the only way to read the EIP register is to execute a call instruction and then read the value of the return instruction. So there's a pointer in the stack. That's the return instruction pointer, which has the return, well, the instruction pointer itself whenever we push the stack. You know what I mean? Oh, okay. Okay, that makes sense. I see. I mean, I can write this for you. It's pretty simple. I mean, it's kind of really trivial, I guess. Let me open this. Where is Milton? Where is Milton? Mr. Milton, open yourself. Milton. Okay, so if I decide to move this a little bit, and then I decide to write something, the thing that I was like thinking, okay, well, how do we get then the EIP back from the getFrame context itself? You know, because if you remember, we have in the code we have this getFrame context, and what basically it tells you is that the getFrame context function from Windows, what basically does is this. I mean, it's kind of it's kind of interesting. So imagine that you have a set of instructions, of assembly instructions, and we have I don't know, some move, whatever, some move. I mean, I'm not gonna tell you what I'm doing here, but I just want to put some examples. And you know, and probably you want to know the another move here. You know, another move. And for example, you want to know the instruction pointer that was here. This is this instruction pointer. So I mean, the only way to do that is if we by itself, I mean, imagine that here we have a call stack, and probably, I mean, this is totally wrong, but I mean, this is just for my representation. Imagine that here we are in a function, but we want to know the instruction pointer that's in here. But this, I mean, we just have this. Well, we just have this one, you know, because this is the what can I say, the base for the process stack, you know, and all of these ones are offsets from the base stack, you know. So if you want to know this, we will need to have to calculate the offset itself, or if we cannot do that, we can just make a transformation here in the code, so that instead of executing this instruction, what we do is execute call. I mean, we just do call, and what call is going to do is going to push on the stack, on the process stack, and it's going to tell it's going to store in its return instruction pointer the instruction pointer It's gonna have here some kind of it's gonna store the RIP at the place that we want. So it's gonna calculate it for us. You know, it's gonna have some IIP plus some offset. You know, it's gonna be this RIP is gonna be equal to IIP plus some offset. Which is what we want, and this is like this kind of tricky thing. Oh, all right, that makes sense, and probably that makes sense because I mean you probably don't know what's gonna happen to the code itself, because you don't know if this is a branch, or you don't know if uh, um, well, yeah, I mean depends, because if it's totally deterministic, you could do it. Yeah, something like that, I guess. Well, but that's a way, you know, to get the instruction pointer, and probably that's what the get for context function from Windows does, so we can get the context and return together RIP on that place, you know, which is kind of interesting because I mean, so how how was that possible? I mean, if we kind of modify this instruction pointer directly, how does Windows do it? Oh, okay. So probably it's like this. I mean, we use a return instruction, so we can set the instruction pointer back. So it's like this kind of crazy thing, isn't it? Because now, I mean, if we want to set the instruction pointer to something, we have to call return or iret. And you know, I mean, probably that makes sense, you know, because Jesus, well, that's good. Uh, so we can modify this and then call this, and the instruction pointer will be modified. So that's interesting. So how does it work? I mean, if we have perfection on the processor, how do we know which one is which one is the one that's like currently working on? Is it the so I was okay, an instruction address read from the bus during an instruction load, which that means it's not gonna match the value of an EIP register, even though the different register. Okay, we have to read a little bit more on prefetching so we can see how does that affect the EIP register. Or I mean, probably we can use the EIP itself. I mean, the EIP is gonna tell us just where is the instruction pointer, but in general, how does prefetch instruction mechanism works? Okay, this is cool. This will answer my question of what are operands. See section 642. Let me copy this here so we can please load it, please. It's not it's not too hard. There are just 4,700 pages and 44. So do your job, man. Okay. I don't know where was I. Right here. We were here. Okay, so we have read almost a chapter. Half a chapter. Please. Right here. Oh, hey. Well, it's not too long, It's not too far away. It's not too far away, We can do this. Procedural linking information, struct frame base pointer. This is the return instruction pointer. But I'm gonna go ahead because everything has an order here, So we're gonna take it whenever we take it. So let me read about this. Okay, the instruction pointer in 64-bit mode is basically the same, just that the 32, the higher the upper 32 bits are going to be reserved, I'll assume. Oh no, sorry, no. I got stuck with the R flags. Yeah. No, this 64-bit mode is gonna work, but it's gonna be linear address space, and it's gonna it's gonna be just that, And you can use a technique called RIP relative addressing, and this technique is the effective address uses to calculate the effective address. We add a displacement to the RIP. which I don't know what does that displacement is, but we can take a look. Operand size and address size attributes. Six five five three six. It's not 64K, it's 65K. Well, I'll assume. And when operating on 32-bit address size attribute, we can get up to 4 gigs of address space. The default operand size. I want to go to this, please. The effect of this prefix applies only to the target instruction. Table 3.4 shows effective operand size and address size. So the deflag encodes segment descriptor. So there's a descriptor, which I don't know where it is, but in the code segment we have a descriptor which has a deflag, which if set, the size prefix 66h. Okay, n is no and y is yes. Okay, so it's a combinatory thing. I didn't understand the table, but yeah, it's less like, okay, the flag can be set or not set. The instruction prefix is present or not present, and then you had the combinatory for each one. So it's these things, you know, it's like 1, 2, 3, 4, 5, 6, 7, 8 combinations, you know, because it's 2 to the 2 to the 2, so it's 2 to the to the cubic power, it's 8. Cool. Okay, which in fact it's not combinations, it's permutations. Well, I don't remember that. So yeah, that's are the combinations, and we can, well yeah, there are permutations because the order, it matters. Okay, so effective operand size. So if we don't have the prefix for the operand size, neither we have the prefix for the address size, which it's just the difference, it's a number. 67h and 66h are the prefixes for operand size and address size per se. So we have if it's no and 0, we have 16 16, then we have 16 32, 32 16, 32 32, 32 32, 32 16, 16 32, and 16 16. Okay, so if we have a flag and we have the size to be, yeah, okay, so the no has more precedence. In this case, if it's a yes, is that it's gonna be 16-bit. If it's a no, it's gonna be 32-bit. In a general way, you know. If it's no, 32. If it's a yes, 16. No, 32. No, 32, 32. If it's a 0, and then yeah, it's a 32, 30. Okay, so also this has more precedence, the D flag, because even though they put yes, so it's been 16, it's not valid, and here it's not precedent. Or are they the opposite? Yeah, probably they are the opposite, because now if the flag is 0, that means that they are gonna be 32 when they say yes, you know. Now they are 32 when they say yes, and they are 16 when they say no. You see? Oh, okay. Okay. Okay, I got you, Mr. Table. Okay. Okay, so here's where he's gonna explain the whole the operand stuff. Okay, cool. All right, so man, this was getting really interesting. Okay, so we'll need to stop right here, but if you are so excited as me as to follow on what's gonna happen to the operand size and address size in 64-bit mode, please hold on, and we will check that on the next stream. So as for today, please, if you have any questions, ask them and I'll be happy to answer them. Yep. You can ask them on Twitch or on YouTube or on Twitter. And I think that would be all. So, yep. Yeah, I know it's gonna be really, really fun to do this, you know. And I can say that it's all for today, and I will see you all guys on the next stream.